The fourth lab in Physics 2212 was macroscopic view of DC and RC circuits. The purpose of this lab was to learn how to use multimeters and measure the potential differences of conventional currents. Also was to differentiate behavior of ohmic resistors and capacitors. Some of the physics principles that were explored included currents, which can be modeled through I equals delta V over R, energy conservation, and charge conservation. Energy conservation deals with the loop rule. Loops are closed circuits, and in loops, the sum of charges and potential must be zero. Charge conservation talks about nodes, which are junctions in the currents, and how at any node in an electrical circuit, sum of the currents flowing into must equal the currents flowing out of that node. In this lab, we utilized Circuit Construction Kit to look at the potential differences across different circuits. We also used a voltmeter and specific locations to look at the currents and potential differences. Listed are some of the materials that we used for this lab. In part 1, it asks you to predict I1 and I2 based on a diagram, with the batteries being at 1.5 volts. Based on node rule, we know that I1 should equal I2. And using the formula 2 times E times M times F minus I1 times R1 minus I2 times R2 equals 0, we find that both I1 and I2 are equal to 0.0204. This is 0.0004 away from the modeled expression where we got 0.02 amps. In part 3, it asks you to replace the existing ammeter with a voltmeter, with the voltmeter having a voltage of 3 volts. And in part 4, you were to observe and record potential differences in the circuit. On the right, I have written the different potential differences across different locations on the circuit. As you would expect, since it is a closed loop, the sum of all of the different potential differences across each of the positions sums up to equal 0. The next part asks us to graph the potential versus the position, and then asks us why the voltmeter does not change ammeter, and this is because its impact is negligible, but it does alter the circuit. In part 7 of the experiment, the ammeter replaces voltmeter in parallel with the 100 ohm resistor. The current ended up splitting because there was no resistance, and I equaled 0.06 amps. In part A, using the formula R equals delta V over I, you must solve for R at different locations across the circuit. I got R 47 ohm equals 47.95, R of 100 ohm equals 102.05 ohms, R of the wire equals 0 ohms, and R of the ammeter equals 0 ohms. The next half of the experiment deals with RC circuits, using a 10 ohm bulb, a 200 mF capacitor, and a 9 voltage battery. On the chart, I have given the time to charge and the time to discharge at 10 ohms and 20 ohms. Next, I recorded my observation with a 30 ohm bulb, a 200 mF capacitor, and a 9 voltage battery, in which the current flowed counterclockwise while discharge occurred, and it was fast at first but then slowed down. On this slide, I have graphed my RC circuit ln delta V over delta O versus time. As you can see, it is a linear, negatively sloped line, and using formulas for earlier in this experiment, delta V equals delta V initial times E to the negative T over RC, you can solve for RC using the slope of the line that we just created. The slope of my line equaled negative 0.1674. Plugging this into M equals negative 1 over RC, you get an RC value of 5.974 seconds. Compared to the CCK value of 6 seconds, I ended up getting a difference of 0.02 seconds of my RC value of the experimental versus the computational model. When asked if we were doing this lab in real life, how would it change? Well, the ammeter would actually have a slight resistance, which would create smaller current readings, and the circuits would not have as precise of measurements, and the voltage versus time graphs would have more variance. Additionally, if the batteries were real batteries and they're real capacitors, the actual batteries and circuit components would have an internal resistance, so it would take longer for the models to charge.